Hello again, this is Tim Baldridge, and welcome to section 2 of Building Odin, where we're designing a embedded um, logic language for Clojure. I wanted to talk a little bit about this first too, and talk about how what we're building is not so much focused upon the idea of relational programming, of being able to run programs backwards and that sort of thing. Instead, what we're really focusing on is kind of a toolkit for building query languages, building maybe some rule systems and that sort of thing. And really a focus on composability and extensibility as well. And so we're not going to put over the top of this necessarily. We may just for the learning experience, but we're not really going to focus on putting over the top of this some sort of specialized text-based syntax that will parse or something. I mean, we could do that, but we're not going to do that. That's not one of the main focuses. The focuses here is embedded, something that you can just download this library and use it to query almost any data source. All right, so let's talk about this a little bit. I think we've discussed this in previous logic programming tutorials, but what we're going to do is we're going to view our program, the execution of this program, as a stream of environments. And as we talked about before, the environments are basically hash maps. And so what we're going to have is we're going to have a transduce, and then we're going to have our program, and then we're going to have something that we're going to do with the resulting environments like conj. And then the input is just going to be something like this, a vector with a single hash map. So we put one environment in, and we get either no environments or perhaps one or more environments out, which are the solutions to our program. So as an example of this, we can start off by defining equals equals a and this is just going to show an example of simple unification. Equals equals is going to call this unify function, but we don't have to pass in the environment. The environment will be this stream, right? So what we're going to just do is call keep, and keep is going to hand us a bunch of environments, right? It's kind of like maps. So we have an environment like this, and we're just going to unify the environment with A and B. And so this will return a new environment, which kind of continues along in our either filters out things from our stream or just passes environments that pass. So now we can write a simple program. Let's go down here and bring this up so we can perhaps see it a little better. So we can now write a simple program. Let's say A equals 1, and let A be an LVAR. And let's see here. The error we get equals. There we go. There we go. So what we get out that this LVAR A is our answer, right? That our answer, in fact, equals 1. And in fact, we can comp onto that something that kind of pulls out that logic variable at the end. So what we can do is we can say keep, and we're going to, our function is going to be an environment. We get an environment, and we're just going to walk the environment finding A, right? So this is kind of a projection. What we would get back now is a list of possible values of A, and as we see in this case, A is only ever equal to 1, and so therefore that's our only result. And this is fairly composable, right? We can go up here and we can say def prog is this, and we would need we could say def A is that's the thing we're searching for, right? There's nothing stopping us from doing that. In fact, let's put this in a def n. So we're going to parameterize our function, if you will, with prog, which is then handed A, like that. There we go. And then we can instantiate our program handing it A, and we get the same result. So already we have this composability here with comp, right? Okay, so the two other things that we need for a logic program like this is just disjunction and conjunction. And we already see an example of conjunction here, and that is we can further filter the stream here. If A doesn't exist in its environment for some reason, then we would filter it out. So it's interesting to note that comp, when we're using transducers, we're looking at transducers as a stream of environments. Comp becomes conjunction. And so we can actually just def conjunction to comp. And that would be an and. So now we can do another one, which is disjunction. And this becomes a little bit more difficult. This is a logical OR. And we're going to have one or more expressions, right? Now what we have to do here is we have to create a transducer. And so let's get to work on that. So the first thing we're going to get back is this XF, and we'll fill out this let in a little bit. And then we have the inner part of our transducer, which is just the standard pass-through format. So if we get an accumulator, so on and so forth, ACK and item. Now here's where it gets fun. What we want to do, what a disjunction is like, is trying each one of these branches, right? So we could say here that our program is a disjunction of A being 1 or A being 2, right? And well, we've done this in some of these other tutorials. But what I kind of came to the realization of when working through this for the 10th time or something is that really what this disjunction becomes is nothing more than a reduce, but reduce over the functions, the expressions here. So what we're going to do is we're going to pre-process these expressions, handing them the XF. Right, so these expressions here are transducer functions that will expect this XF, and we're going to pass into them our values. So we're going to call this FS, and then we're going to do map V, and what we're going to do each time here is we would call the expr. So we want to hand the expr XF, and then like so. Now there is a problem, and that is it's kind of hard to explain. So maybe we could draw a graph or something like this. But what we're going to have is our input here, our input environment, and then that's going to end up becoming two separate outputs, and those outputs are two branches of this tree. One being that A equals 1, and the other being that A equals 2, right? So these are our two branches, if you will, pardon my ASCII graphics, of this. So we want to try one, then the other. Now each one of these is then going to call our XF, our same XF function. So we kind of have this thing like this. They both end up calling XF. So the problem is that if XF here, farther on, is something like take, it may terminate. Right, and so we want to make sure that we preserve the reduce signal from the reduction, and that preserving reduced is what we need. So I'll show you here. The inner part of this is basically just going to be a reduce of something, and then our input, our initial accumulator, is the accumulator, and then our FS our functions. So we need to call each one of these functions with the value, and that it just ends up being 2, 1 item, right? So we're going to call each item, each one of these items, which is a function, passing in our current accumulator, and then we are going to also pass in the item, right? So we're trying these functions. Now the problem is that if this call here returns reduced, it will terminate this loop, but would not necessarily terminate any disjunctions above us, because this reduce will strip out that reduced marker. And what I'm talking about there is this sort of thing. In a reduce, I'm not sure if you're aware of this or not, within a reduce you can just call something like this, and it doesn't matter what I put into this now. This is a reducing function, and we'll start with nil as our accumulator, and then we'll give it range of 10. So whatever happens, this just returns reduced of hey, right? And that's our result. So at any time you can say reduced, you'll terminate the reduce loop, and that's how taken those things work with transducers. So that's what we're doing here. Is we're going through each one of these functions, passing them the item, and then continuing on. Now, what we need to do though is we need to wrap this here with preserving reduced. Now, preserving reduced is unfortunately a private var in Clojure core. So we're going to kind of hack it here by saying give us the var and call that itself. This is a hack, but it does work. There we go. And we can take a look at this. But basically all it does is that it calls a reducing function, and if the result is reduced, then we rewrap it with reduced. Otherwise we return the value. So it's just a way to make sure that if any of these reducing functions return reduced, that we continue that on outside of our reducing function. Okay, so that just accept that we need this for now. And we could probably copy preserve and reduced in, or we should probably create a ticket to see if we can make that public, but whatever. We're fine with this for now. So now we have our program, and what's our result? 1 and 2. Right? So this disjunction is trying to say that a equals 1, and then a equals 2. Now, because of this conjunction, we can just go and create another clause of our program here, prog a, and then we can actually say where a equals 1, right? And then we have what do you know? The only result is 1, so we've limited our result. Okay, so one last thing I want to talk about, and that is functions that would perhaps query a data source. So we're going to make a very simple data source today, and this data source is just range table. We don't have a better name right now. But what this is going to do is the first arg is going to be the count of C, and then the output is I. Right, so this will take 2 logic variables, and it will count from 0 to C and bind that to I each time as it goes along. Now, this is a lot of these functions I'm going to show you today are not necessarily reversible. You can't just go and say, you know, here's 4, get me what the max bounds are for this. I mean, that's not really going to work. You can't run a lot of these programs backwards. But what I found is that a lot of times I don't really want to. I'm going to run my programs a certain way, perhaps run some rules backwards. That's acceptable. But some of this high-level logic programming stuff I don't really often use, and so we're not going to focus on that. So what we're going to do is we're going to accept a single environment, and then we are going to output multiple items for that, right? So this single environment, because we are returning multiple items, we have a map cat. So now we have an environment, and we need to look up the value of C in that environment. So we're going to call this C prime and walk in our environment C. Now we're going to assert that not lvar C prime. So this is going to make sure that C prime is not unbound, and we can even say C must be bound, and we'll see how this works out in a little bit. So now what we have is we need to return multiple items, right? And that's basically a range over C. So now we have a lazy seek of this. Now when I did this sort of thing before, what I didn't like was having to do something like this for item in this. We are going to emit a bunch of environments where we're going to unify we're going to unify the environment so that I is equal to item, right? Now this works just fine, but there is a problem with it, and we'll take a look in just a little bit here. So let's just switch our program here. In fact, let's cut out program and call this range table of 10 and A. And what do we get out? Well, we get the numbers 0 through 9, right? So we're kind of injecting 0 through 9 into A. Now, I said there's a problem with this, and there is a problem, and that is map cat here is a transducer. Everything is transducers, and yet here we have this collection, and we're going back to a lazy seek. And I really didn't like the fact that we had all these intermediate variables being built up just because we needed to return a Clojure collection. And if we look at map cat, it actually says F should return a collection. Now, if we actually dig into this, though, map cat ends up calling, the transducer version calls cat. And if we look at what cat does, well, cat calls reduce. So the idea that it needs a collection, and we can kind of dig into that and say, what really does that mean with collection? What it means is something that is reducible. Well, it just so happens that in Clojure, there is this thing called eduction. And what eduction does is just bind a transducer to a collection, but it doesn't actually it's more of a way that when you do a reduce over this sort of thing, over this collection, it's going to kind of run transduce over the items as it returns them in the reducing function. Now, that's really kind of hard to understand, but the fact is that something like range now actually results in this Clojure Lang long range these days. And this, when we call reduce over this, it's not actually creating a lazy sequence anymore. It's just a loop. In fact, we can probably find that. Let's see here, reduce. Here we go. So this reduce is just a loop where it calls the function every time. So what's going to happen with our reduction is that we can go range C. And as we reduce over this thing and we go back to that loop, as this loop is being called here, each time it calls this invoke, what that's actually going to do is invoke our transducer function and then continue on invoking the rest of our chain. So it's a lot more efficient. Okay, so now that we have eduction, what we're going to do next is we are going to go here to this, which is just keep fn, and we have our item, and then we're just going to unify env I and item. And what do you know, that can actually be even clearer like this, so we don't have to name item anymore, and we can just cut that out and cut that out, and there we go. So we're returning this eduction of keeping the partial. In fact, let's put them on the same line. I kind of like the way that looks. There we go. And let's run it. Boom. Exactly the same result. So this could be anything, right? And we could have multiple variables here. We just walk them first, and then we could do things like query the disk, right? We could say, files, a path to a file and the file name, something along those lines. And then we could use that in our logic program. Alrighty, so and then we can filter this as well. We can say a equals a. A is 9 or something like that, and now we've only gotten 9 back because we had this table, but it got filtered down with 9 because of the unification process. Alright, so that's pretty much all I had for today's tutorial. In the next tutorial, we're going to go on to some other fun macros that we can build using this. Macros that provide a clearer interface for wrapping this up here. And I call those for queries. We may rename that. And then there's also pass and project. We will build those as well, which allow us to, so currently we have a way to put logic programs into our Clojure program. And those other macros I talked about are ways to inject Clojure into our logic language and kind of mix and match. And it comes out quite clear, I think. So that's the tutorial for today. Thank you so much for watching.